us. I am excited to introduce today's speaker, who is Dr. McKinley Brumback. McKinley is currently a postdoc at Caltech, and previously she it feels like but it's been a couple of years now, she got her PhD from Dartmouth in 2020, and she's going to tell us all about accretion disks on neutron stars. So take it away, McKinley.
All right, thank you. Thanks very much, Kristen, and thank you to everybody for coming and for the chance to chat with you all today about my research. I'm excited to share what I do with all of you. Feel free to call out any questions as you have them. I have what I think is a good Zoom setup, but when displaying PowerPoint as well, it can always be a little tricky to see if anybody's raising their hands or something. So don't be afraid to interrupt me as we go along. And my usual other disclaimer is that my dog doesn't like the mailman, and when the mail is delivered, there's usually barking on my side of things. So apologies if that happens, but it's all fine. So like Kristen said, I am a postdoc at Caltech. I work with Professor Fiona Harrison and the NuSTAR group doing high energy astrophysics research. And I'm here to tell you about the research that I did at graduate school at Dartmouth and have continued at Caltech working on neutron stars and magnetic accretion processes. And so I'm just very interested in how gas behaves when it's interacting with really strong magnetic and gravitational fields. And a lot of this research has been done in collaboration with many members of the NuSTAR science team and the NuSTAR galactic binaries working group. And I've listed some of the names of my primary collaborators below. So I'm kind of interested in, like I said, the strong gravity, strong magnetic field effect on matter, and what this can tell us about the most important, the most extreme objects in the universe. So one of the most extreme objects in the universe that's of personal interest to me these days is the ultra-luminous X-ray pulsars. So I'm going to start off my talk with a introduction that kind of leans on the ultra-luminous X-ray pulsars as a intro to this field and why I think that that's a particularly interesting bridge. And then I'll talk about my own research and how we can study unusual behaviors in typical accreting pulsars to learn more about the unusual behaviors in their more extreme counterparts. And I'll look specifically at suborbital modulation from warped accretion disks. And then I'll end by talking about some of the current and ongoing work that's been happening with some summer students I've had at Caltech, doing a follow-up study with nicer pulse profiles. So to begin, the types of objects that I study are accreting neutron stars. The neutron stars form inside massive stars, which develop these dense, heavy cores. And when they explode as supernovas, they can leave behind compact objects like neutron stars. And neutron stars are some of the most magnetic objects in the universe. They can have magnetic fields up to 10 to the 12, even higher, 10 to the 12 Gauss, and even higher for magnetars. And these kinds of magnetic fields are completely impossible to recreate in Earth-based laboratories. So if we want to study how gas interacts with strong magnetic fields, we have to go study it at the source at neutron stars. And the way we get gas interacting with these neutron stars is when you have an accreting neutron star or an accreting X-ray binary, as they're also called. And this happens when you have a neutron star with a companion star that is donating material by one way or another. It can be a massive star that's undergoing wind loss, and some of that material that's blown away in the winds can fall onto the neutron star, or it can be smaller stars undergoing Roche-Lobe overflow. And that's kind of what's shown in the image on the left, the artist's rendition on the left. And the gas will travel down towards the neutron star, heating up as it falls down the gravitational potential well and forming an accretion disk. But when the accretion disk reaches the magnetic radius or the alphane radius of the neutron star, the disk gets truncated. And that's what's shown in the artist's rendition on the right, where we see this area of space that does not have gas immediately around the neutron star. And this is because at this point, the magnetic pressure exceeds the ram pressure of the disk. And so we actually have matter that is now confined to field lines and funneled onto the north and south poles of the neutron star. We've got kind of a theoretical idea of what that might look like. These are two different simulations, one by Romanova and one by Parfrey. And these are just two looks at what the magnetic dominated accretion might look like, where we create these accretion streams or accretion flows that kind of funnel gas from the accretion disk along field lines and onto effectively the north and south magnetic poles of the pulsar or the neutron star. And so we have these MHD simulations, which can give us a theoretical look at what these kinds of structures might look like and what kinds of physics might be at play. But it's important to back up these simulations with observational data of what's happening in real sources. So that's kind of where my project is coming in. I'm hoping to study the accretion flows in neutron stars to kind of get an observational counterpoint to these kinds of theoretical simulations. So the ideal place to conduct such a study is a pulsar. And probably everybody knows this, but I always say that, you know, it's kind of one of these squares versus rectangles situations. All pulsars are neutron stars, but not all neutron stars are pulsars. And a pulsar is just a neutron star where the magnetic axis is aligned so that as it rotates and sweeps across space, it is oriented towards Earth at some point, and we see a bright flash of X-ray radiation. We see this flash because the magnetic beams are accelerating particles up along them. We've got non-thermal processes like Compton upscattering that is creating this huge energetic beam of radiation that sweeps across space, much like a lighthouse. And you can kind of see that effect in this simulated pulsar image, that when the accretion stream and the magnetic beam is pointed towards you, you get a bright flash of emission. And when it's oriented away, you get a slightly more dim view. And when we see these types of sources, one of the very first things we observe is the pulse period. And if we observe them with an X-ray telescope and then fold that data on the pulse period, you get what's called a pulse profile. And so this is just an example pulse profile, one that I pulled from my own research. But the shape and the configuration of the pulse profile are directly related to the geometry and the emission mechanisms of the accretion flow and the accretion column, right where the gas is trapped in this extreme magnetic field. So I've been doing a lot of studying how the shape of the pulse profile is related to changes in emission geometry. This is why, this is just one reason why pulsars are an excellent place to study magnetic accretion mechanisms, because we can actually really see the effects imprinted on the pulse profiles. But there have been some challenges to doing these kinds of studies, and one is trying to understand this extreme population of pulsars known as the ultra-luminous X-ray pulsars. And the problem with these sources is that they're not really behaving in ways that we expect pulsars to behave. They're much too bright. So when I say they're too bright, I mean that, like, generally in X-ray astronomy, the brightness of a source can give you a loose estimation of the mass of the accretor. And this is because if we assume that an object is actually accreting gas, so in my little schematic diagram, if big M is drawing in a cloud of hydrogen gas, little m, that at the very maximum, it has to balance radiation pressure with gravitational force. In order to actually accrete that gas, the gravitational force must be greater. So this allows us to balance these forces and set up an inequality, which is effectively a function of one variable, the mass of the accretor, big M. And this is called the Eddington limit, or the Eddington luminosity, that says this is how bright an object can shine, an object of a given mass can shine while staying in hydrodynamic equilibrium. And this is very much just a theoretical limit, but it gives astronomers just a broad brush stroke at, are we looking at a neutron star? Are we looking at a black hole? And it can be helpful for kind of assessing the type of object that we're dealing with. So when we look at things in the X-ray wavelengths and assess their luminosity, we get this kind of luminosity scale, which I've represented on the right here, where anything that is 10 to the 38 ergs per second in luminosity or below is likely either a neutron star or maybe a very bright white dwarf that is accreting. And anything that is above 10 to the 44 ergs per second is likely a supermassive black hole, so weighing, millions of times the mass of the sun. And this intermediate range of roughly 10 to the 39 to 10 to the 43 ergs per second is just called an ultra-luminous X-ray source. And it's just a classification of like the objects that are this bright are called these ULX sources. And if we follow the Eddington limit and reverse backwards, these accretors should have masses tens to hundreds to thousands of times the mass of the sun. And this kind of plants them firmly in the we expect these to be black holes realm, since neutron stars are not thought to be able to grow much above 3 solar masses. So that was kind of the accepted, view of the field, that these ULX sources were mostly accreting black holes of intermediate mass, until 2014, when Matteo Becchetti and his team detected pulsations from an ultra-luminous X-ray source. This was M82X2, and they found coherent pulsations which can only arise from the rotation of a strong magnetic field, which indicated that this object was not a black hole, since black holes don't have the magnetic fields capable of reproducing these pulsations. It was most likely a neutron star accreting hundreds of times more rapidly and shining more brightly than we understand that it should be. And with a detection rate of roughly about 1 per year, the ULX Pulsar sample has continued to grow. All of these sources are accreting at hundreds of times their Eddington limit and have been continuing to do so, since their discovery, which just doesn't fit with what we understood accretion physics to be. These sources, maybe they should be able to undergo a very short-term extreme accretion event, but they are accreting so strongly that how are they sustaining accretion at all? They should effectively be blowing away all the gas around them with the power of light that they're emitting, but they are sustaining this super Eddington accretion on long time scales. And so this is, I think, just a really interesting point for high energy astrophysics at this time, to take a look at this sample of sources that is doing something that we don't have a lot of mechanisms to explain why, and realize that this extreme behavior is actually commonplace, and it's just we who don't understand it. So the ultraluminous X-ray pulsars have a bunch of interesting properties in addition to the fact that they're just extremely luminous. They also show, a number of them show pulsation transients, which is where the pulses seem to come and go. They're visible at during some observations and not during other observations. And more than half of the sources also show a superorbital period. This is a periodic change in brightness on timescales longer than their orbital period. And for some sources, the orbital period is not known, so it's not sure if whether any modulation being seen is orbital or superorbital, but for these that I've listed, this is a confirmed superorbital period, so it seems to be a relatively common behavior. And finally, there's the fact that their spectra have really similar properties in that they all are quite soft in the X-rays. So this is a figure from Walton et al. 2018, looking at these 12 different ultraluminous X-ray source spectra. And 3 of these are ultraluminous X-ray pulsars. The others are just unconfirmed. They have not had pulsations detected, so it's not confirmed what the compact object is, but it was presumed black holes. And this begs the question, if the accretor is different, then we should see some differences inherent in the spectra, but from this image with the labels taken out, it's almost impossible to tell which 3, are a subgroup. If anybody's curious about which are actually the ultraluminous X-ray pulsars, it's these three. So this is just, I think, an interesting point that really emphasizes the fact that it's important to study these sources to learn more about super Eddington accretion. But the ultraluminous X-ray sources are mostly extragalactic and quite faint. It can be really challenging to study them, despite the fact that they're accreting in such an extreme fashion. So it would be wonderful to find similar sources that we could study that were a little bit, less observationally challenging. So if the questions are, what are the physical mechanisms behind extreme super Eddington accretion, then we might ask, where can we study super Eddington accretion and some of these unusual behaviors like pulsation transients and superorbital periods in pulsars that are closer to home and galactic, and maybe not in this ultraluminous X-ray category, but have similar properties. So this was a big chunk of my thesis, trying to bridge the gap between what I call typical, by which I mean just a bright X-ray binary, a bright galactic X-ray binary, and the ultraluminous X-ray pulsars. And I focused on this with two different behaviors that both populations can display: superorbital periods and pulsation transients. And I'm going to focus on superorbital periods for the purpose of this talk, but I do have some supplementary slides about pulsation transients if anybody's curious later and would like to talk more about that. I'd be more than happy to. So the sources that I examined were mainly these three: LMC X-4, SMC X-1, and Hercules X-1. And these are all bright X-ray binaries, either in our galaxy or in the Magellanic Clouds, that have luminosities right around their own Eddington limits based on the mass of the neutron star. Especially LMC X-4 and SMC X-1, they are can have flares that take them into super Eddington accretion regimes. And all three of these sources have a spin period, the rotation period of the pulsar, a known orbital period. They're all eclipsing binaries, so their orbit is very well defined, and established superorbital periods. That's the last number for each source. And so you'll see it's roughly 30 days for LMC X-4 and Hercules X-1, and ranges between 40 and 60 days for SMC X-1. So the cause of these superorbital periods in these sources is thought to be a warped precessing accretion disk that is partially obscuring the pulsar. So this is thought to happen when the accretion disk, which you can see on the right, is kind of warped up out of the plane so that as the disk moves, it is periodically blocking the accretor, causing the luminosity to drop, and then the disk will move out of the way again and the luminosity will increase. What's shown on the left is a 13-year RXTE light curve from LMC X-4, where the black is the RXTE data and the pink is an overlaid 30-day sinusoid. And so you can really see how stable and regular the behavior is in this source. And just to give a little bit more context, this on the right is actually a video for Hercules X-1, so a different source than the one on the left. But the disk will precess, and on the bottom panel, you're tracing out the shape of this superorbital cycle. So it starts out with the disk out of the way, you get full brightness, the disk moves out of the way and you enter a low state. And then in Hercules X-1, there's this short rebrightening called a second on or a short on, where you get a brief rebrightening before going into a faint state again and entering finally back into the bright main on bright state. So this laboratory of these sources that have a warped inner accretion disk that is directly affecting this long-term behavior is a great place for us to actually study how the disk is interacting with the magnetic field, interacting with the beam of the pulsar, and try to analyze this behavior in more detail. And where my thesis came in is that in the past, these sources had been examined with, kind of singular telescopes, mostly in the middle X-ray band, and there had not been a ton of coverage in a broad X-ray wavelength. So my observations were using broadband coverage with XMM Newton, a soft X-ray telescope, and NuSTAR to look simultaneously. And the power of this method is that the neutron star is, excuse me, spam call. The neutron star in the center is rotating, and that magnetic beam is sweeping around, and the observer is seeing it as hard pulsations, but that beam is also shining on the accretion disk, and the accretion disk is reprocessing and re-emitting radiation at much softer, lower energy X-ray wavelengths. So there really are two pulsation signals here that can only be disentangled with broad X-ray coverage. When you can fully constrain the hard X-ray emission, you can assign that to the actual beam of the pulsar, and the soft X-ray emission below 1 keV is mostly the reprocessed emission from the disk. So this was the main goal of most of my thesis projects, to look at these three sources during a single superorbital cycle and watch what happened to the shapes of the hard pulses and the shapes of the soft pulses, and see if we could monitor disk precession and determine, is this mechanism, the warped disk, really responsible for this behavior, and can we observe a complete precession with broadband X-ray coverage? So I'll kind of step through the data, and I'm going to use LMC X-4 as an example, but I did do the same analysis with the other two sources as well. I just won't show so many repetitive plots. This is a maxi light curve in black with the kind of average light curve over plotted in red of the time in 2015 where our data for LMC X-4 came from. And we had 4 observations, each of 20 kiloseconds, and all 4 of them were joint with NuSTAR and XMM. And the key part of this observational scheme is that observation 1 and observation 4 are at the same superorbital phase, the same point in the superorbital cycle. And if the disk precession is really what's driving changes in the pulse profiles, then sampling at the same phase, meaning the same rotation angle of the disk, should show us the same behavior. So this was a very clear hypothesis that we were hoping to test. These are the 4 pulse profiles. And the first thing I want to point out are the changes in relative phase. In the first panel from our observation 1, we have the blue NuSTAR high energy pulses. These are 8 to 60 keV pulse profiles, completely out of phase with the soft XMM half to 1 keV pulse profiles. The same holds true into observation 2, where they are still 180 degrees out of phase, although there are changes to the shape of the pulse profiles. And by observation 3, the pulses are almost completely in phase with one another. So here we're actually seeing disk precession, which is really, really exciting. By the last observation, observation 4, again, we have moved out of phase with the pulse profiles. And the reason why the relative phase is so important is because the soft pulse profiles are originating from this warped inner edge of the accretion disk, and that disk is moving relative to the source of the hard pulses, the neutron star at the center of the system. So we expect that as the source of the soft pulses is changing its position, that we're seeing that show up in a relative phase shift. And we ultimately do see that, which is really successful and really promising that these sources do have a warped inner accretion disk, and that is the cause of these behaviors. But in order to fully test this, we wanted to go model whether these pulse profiles really did hold up with what could be expected from precession of a warped inner accretion disk. So we used a very simple geometric warped disk model. This was something first employed by Hickox and Vertilek 2005, which I later adapted to this work. You essentially define two systems. You define a neutron star, which is shown in the inset, where you assign beam profile shapes on the neutron star surface, and you assign two beams. They can be various widths, they can be various sizes, and they can be anywhere on the neutron star surface. And then you define a disk that is going to precess around the neutron star, which is defined by inner and outer radii, as well as tilt angles for the inner and outer disk. And this together creates your warped disk surface. So I tweaked the parameters of the beams and the disk and essentially ran simulations until I found shapes that matched both the overall shape of the pulse profile and the relative phase of the hard and soft pulse profile, because the code is collecting the hard and soft pulse profile separately. It gets the hard pulse profile just from the pulsar section, and then it observes, what is viewable to the observer from the disk portion to create the soft pulse profile. And so on the right, I've showed two of my observations a little bit larger, where the data in red and blue is overlaid with the simulated pulses. And you can see that the fit is pretty good. I was very pleased with this. It's not 100% perfect. You can see that, especially in observation 3, there's kind of a small extra simulated bump for the soft pulse profiles. And I can definitely talk more about that if anybody has questions. But essentially, I think that we found very good fits to the behavior. And I should say that the key here is that we were not changing the disk parameters between these runs. The disk was remaining the same, and we just allowed the disk to precess and came out with simulations that matched our observations. So this is kind of the larger version of the plots on the previous slide, just for completeness to show the entire thing. Each column is the observations 1 through 4. The top blue panel is the hard pulses, and the bottom red panels are the pulse profiles at different precession angles of the disk. And what you can see is that I've highlighted in green the best disk precession angle that fits our observed pulse profiles. And we're actually fully tracking disk precession here. We have a disk that starts at 0.75, moves to 0.875, comes all the way around and goes back to 0.125 and ends essentially right where it began at 0.625. And the power of this code is not just that we're matching the pulse profiles and seeing, okay, a modeled warped disk can reproduce observed pulse profiles. We can then extract, what does that disk look like? And so these are the disk images for my best fit pulse profiles for LMC X-4, giving us actual potential snapshots of what the disk configuration could look like during its various precession angles. And so if you do this at a high enough cadence, you can effectively get a movie of the disk precessing around, which is really, really fun. So this was the main result from LMC X-4, and I do want to show the SMC X-1 and Hercules X-1 as well, but I'm just going to skip to the end plots here rather than re-show all of the same ones together for the sake of time. The SMC X-1 and Hercules X-1 projects both had some observational challenges where we only ended up having 3 observations in the series instead of 4. So that's why there's only 3 disk images here, but you can still see disk precession, the disk returning to the same configuration in the first observation as it did in the last observation. And you can also see that the disk shapes are different from one another, that these sources have different configurations. So something I would love to do in the future is take this warped disk model and apply this directly to the ultra-luminous X-ray pulsars. To my knowledge, this isn't something that's been done before, but we do have broadband pulse profile information from the ultra-luminous X-ray pulsars. And so there's no reason why we couldn't run this warped disk model on those pulse profiles and see if a warped precessing accretion disk could be a plausible explanation for the superorbital cycle in those sources as well, which I think would be really interesting. So to kind of summarize this, these many projects all together, I'd say that the key results are that we did see changes in relative phase of the pulse profiles in the hard and soft X-ray band that were consistent with warped precessing accretion disk. And something that I did not mention previously, but that came up in all of these observations, is that there was a strong preference for non-antipodal beam geometry. So an antipodal beam is exactly what's shown in this small figure here. It's your traditional dipolar field, North Pole on one hemisphere, South Pole 180 degrees away on the other hemisphere. And it is, a very simplified and iconic picture of what we imagine a neutron star's magnetic field must look like. But in all three of my simulations, because I was also simulating the beam geometry and where they were on the neutron star surface, those beams, in fact, I was not able to get good fits to my observed pulse profiles if I used antipodal beams. The data strongly preferred non-antipodal beam geometry. And this plot on the right is just one example of that from the Hercules X-1 data. So the blue and black points are the actual observed pulse profiles from the first and last observation of Hercules X-1 in the series that I did. And the light gray points are simulated hard pulse profile beams using an antipolar beam geometry. And you can see that that profile is strongly different from what the pulse profile shape actually is. And this was true in all of them, but Hercules X-1, I thought, showed a really nice, strong example. This is something that I think is gaining more and more interest in studies of magnetic accretion, this idea that we've kind of oversimplified the way we think of neutron star magnetic fields. And it seems highly likely that the fields are much more complicated than we give them credit for, and is really interesting and has been seen in several different results as well. So where I've been kind of hoping to take these results recently, and what I'm still working on, is I saw in this project these changes in pulse profile shape over relatively long timescales. I was examining them on the timescale of a superorbital cycle, so that was 30 days with 4 samples in between there. But what happens to the pulse profiles when you observe on really short timescales? Can we actually see short-term changes in the disk, for example? If the disk has any inhomogeneity in its surface, if it's clumpy or irregular, then you might see on very short timescales changes in the soft pulse profile that correlate to differences in the disk structure, and we might be able to sample that much more finely. So I propose to follow up on this data set using the nicer X-ray telescope, which is on the ISS and pictured on the right here. And I proposed to cover the high state of Hercules X-1's superorbital cycle with a number of closely spaced nicer observations in order to examine, in particular, the soft pulse profile shape and see if we could see any changes. If we couldn't see any changes, it might imply that the disk is quite smooth. And if we saw lots of rapid changes, it might imply that the disk has a very complicated geometry. So these NICER observations were analyzed by my summer student from last summer, Hongyu Zhang. He is an undergraduate at Hamilton College and worked with me through the summer undergraduate research fellowship that Caltech offered, and has continued to work with me since the summer on finalizing this data set. And so these plots from this page onward are all Hongyu's. And what you can see here is he's looking at the long-term light curve, again in black of the source, and we can see Hercules X-1's superorbital cycle shape, the really bright main-on phase and the smaller short-on phase. And we asked for our observations to fall during the main-on phase, but it can be kind of hard to time these observations. This source can be a little bit irregular. And so we were a little bit unlucky in the timing of the observations. You can see that they fall towards the back half of the main-on phase. And we had 15 observations, and those are the vertical colored lines on the plot. And Hongyu has them plotted in blue, except every 5th observation is plotted in red just to visualize. And one thing Hongyu did was looking very particularly at the small changes in pulse profile shape for the first couple observations that fell during this bright main-on period and had really good statistics. So these are the first and the third observation from that series on the previous page. And these are actually 2 GIFs with each pulse profile is going to step through a very fine energy bin to watch the changes in energy. So I'll go ahead and play the first one. We're starting out in a soft energy band and moving up into NICER's high energy X-ray band. And you can immediately see some dramatic changes that happen in the shape of the pulse profile just as a function of energy. And this is exactly the behavior that we were studying in the previous work, where we have a hard pulse profile with one characteristic shape based on the neutron star beam, and a soft pulse profile with a different characteristic shape based on the disk geometry. And so if we step through the second, we can kind of watch the same progression. I really like watching that main hard pulse peak emerge from the soft profiles. And you can really see in these plots, the power of NICER to get really fine energy bins and really good resolution. So this was great work by NICER and by Hongyu. So for our observations, this is the first on the left, the third on the right, in the middle, and the fourth on the right. This is kind of a summary plot of the GIFs on the previous slide. The black curve is the overall entire NICER band pulse profile. The red is the soft, the blue is intermediate, and the purple is the high energy, which for the NICER band we defined as being 1.4 keV to 10 keV. And you can immediately see the dramatic shape changes between these and the way that the overall pulse profile is kind of an interesting mashup of the shapes of all of these. One other takeaway, though, if you're looking at all the red curves, the red curves show a remarkable amount of similarity. There are some small differences in the middle plots. The red curves seem to have more of a dip at the top instead of a plateau feature. And there seems to be maybe a notch in the slope of this pulse profile as well. But overall, not very dramatic changes in the soft pulse profile. But by comparison, we are seeing some very dramatic changes in the shape of the hard pulse profile, the purple curves at the bottom. Here, observation to observation, there are marked differences in the pulse profile shape. They all kind of retain the broad generic shape, but we're really seeing that there's something changing about the emission geometry of the pulse beam more than the disk. So just some initial thoughts from this observation. It actually seems that these changes happen more in the hard pulse profile than the soft. But unfortunately, we didn't get to do our full analysis with this data set because, as we mentioned, some of the data fell in that low period of the superorbital cycle. luckily, I was able to speak with the NICER team, and they agreed to re-observe the entire observation set so that we can like fully do the science that we hope to do with this project, which is very amazing, and we're very grateful for their efforts. It's been about 9 months, and we still haven't found a good observing window. Hercules X-1 is positioned in a little bit of a challenging spot in the sky for NICER to see, but we are hopeful that we'll soon get an observing window when this data can be retaken. And still to do will be actual modeling of the emission region and more rigorous spectral modeling. So to kind of summarize, this entire project and everything that's been happening, I've been using broadband X-ray observations to constrain accretion disk geometry by studying the pulse profiles, which is, another fancy word for that is just reverberation mapping, essentially, using the observed changes in soft pulse profile to inform a simple warped disk model, and using that to confirm that just precession of the accretion disk can be responsible for the changes that you see in the pulse profiles. And hopefully future work following up on the Hercules X-1 pulse profiles with NICER will really investigate where the changes in the system are coming from and the pulse profile structure in much more detail on shorter timescales. So I will end there, and I'm happy to take any questions from anybody.
That was awesome. Thank you. So I think that if people have questions, they can raise their hand or put it in the chat. And I think people are overcoming their shyness. I was wondering, could you talk a little bit more about, you said that when you modeled one of your sources, you had a little bit of an excess?
Yes, I think that was over here in the observation 3 plots. There's an excess. Is this the one you were talking about?
Yeah.
So this is kind of, I think it's cute and funny because it really points at actually how complicated doing this is. It's very hard to have the model actually fully fit the data in this case. And the model has so many parameters between the angles of the disk and the angles of the beams that it's very difficult to properly sample the entire parameter space. So we take everything that we can, that we already know about the system, such as if we already know the inclination of the orbit from the literature, we'll use those values and freeze those so that we can have as little degeneracy as possible. But essentially what this little extra excess is saying is that just doing 2 beams on the neutron star, even though they're not antipodal in this, they're definitely, I think, I can't remember for this one, at some point I had 2 beams on the same hemisphere, which is, very much what we don't imagine. But even that is kind of insufficient to fully encapsulate the pulse profile, because it's saying, well, we're seeing something from one big beam, we should be seeing a little something from the other beam, but we're not seeing it because it shows up in the model and not in the data. So I always enjoy this discrepancy, even if it means that that ultimately my model probably needs to be a little bit more rigorous and a little bit more physical to fully capture the data. It's a fun problem to have.
It's amusing. Thanks. I see Hope has her hand up.
Yeah, hi. Thank you for the really wonderful talk. I think it's really cool what you're doing. And you may have sort of answered my question just now, but just to make sure I understand, I was unsure when you meant your models were strongly preferring non-antipodal beams. I didn't know how to visualize that in comparison to the antipodal picture. And but you maybe just sort of said something like that, like the beam itself, instead of being on opposite sides, could be kind of like anywhere else on the surface.
Exactly. The exact way that I run this model is that I usually just have the first beam, which would be, you can think of it as the one that's visible in this inset. I just place it on the neutron star surface and define that as 0.0. And I define the second beam completely relative to that beam. So if it was going to be completely antipodal, it would be, 180 degrees in latitude and minus, 60 or so degrees other way, this way longitude, that way latitude. And what I found was if I did that, if I defined the beams to be, one on this side of the neutron star and one on this side of the neutron star, there was no, the other parameters of the size of the beam or the parameters of the disk, there was nothing I could do to make the pulse profiles look like the data. I had to place the beams into non-antipodal geometries. Now, whether it was just, one beam here and one beam slightly off, or whether it was two beams on the same hemisphere, it kind of depended on the observation. But the beams had to change and not be antipodal in order to get any semblance of good fit to the data like I show here. Because when they were confined to being completely antipodal, I went right past it and now we're in the movies. It would be like these fits, as if I was trying to fit the black or blue curve with the gray curve, and you can immediately see just how off it is. So it wasn't a result that I was necessarily looking for, but as I've talked to more people who do similar types of modeling, they're also seeing similar things, which I thought was really cool, that we're all kind of slowly converging on the fact that these magnetic fields are much more complicated than we give them credit for.
Yeah, thank you. That's really fascinating.
Do you want to go ahead, Daryl?
Sure. I guess the most important first question is whether or not your mailman has arrived. But
actually, I don't know if you can hear a little bit of barking. That is my neighbor's dog.
Oh, that's lucky you. Okay.
So we would all know if the mailman was here. I would probably jump a little bit. But okay. We're good for now.
We're good for now. So I'm just, this is a beautiful talk. Thank you for sharing it with all of us. And I share, I hope, sort of fascination with these antipodal beams. But to try a different tack here, you are leveraging so many of our elite X-ray observatories. So XMM, NICER, NuSTAR, et cetera. And I'm wondering, since we have some new missions coming up, close to launch, whether it's Athena or others, I'm wondering if you have a dream observation that could crack some of the uncertainties or some of the interesting questions still left in your models. So what do you need that observatory to do? And do any of these upcoming ones fit the bill?
A dream mission. Wow. What a great question. If I had $1 million, what could I do?
No, billions.
Yeah. If I had $1 million, I still wouldn't have enough for my dream observatory. This is something that I'm very interested to look into in the future, would be trying to leverage what high resolution spectroscopy can add to these models. And this is very much not something that I've had a lot of experience yet. So I'm not sure that I know, exactly what it is that I need, but I think that I've examined a little bit of like XMM RGS data and some, trying to look at like outflows and winds from these sources. I think that could be a really interesting way to look at the disk in kind of a new and complementary way. What is actually going on with the spectroscopy of these disks, and can that tell us anything additional about the geometry? And I also think, in terms of an ideal data set to study disk changes, Kristen's Moose data set, which if anybody doesn't know is a monitoring of SMC X-1 while the disk is in an unstable time and is changing its shape. I think that data set is really primed to give us results about the way the disk is changing its geometry. And I'm very excited to keep working with that data set as well.
Thanks.
Cool. I don't know if I see any other questions, but we'll give people a minute. I thought that this result was really neat too. I'm really surprised by that because I think like a lot of people, we all have this idea that, like neutron star beams go out like this.
It's just taken for granted. It's in all the textbooks, but it's definitely not just me. The main paper that I'm thinking of is actually submitted, not accepted, but Jürgen Wilms's group at Bamberg does a fair amount of very theoretical accretion column modeling. And they have also found that when they model the full profiles, they can't have antipolar beams as well. So it's like definitely not just me coming to this conclusion.
That's always the best feeling, isn't it?
Yes, yeah, definitely.
Hey, McKinley, since I know we have you for a couple more minutes and you and I chatted about this earlier, I'm wondering, I know you have a paper coming up and I don't want you to spill the beans on any of your results, but about stray light in NuSTAR. And I'm just wondering if you could give all of us just a very quick description of what that is and why it's useful.
Absolutely. Oh, I'm totally happy to spill the beans. For what Daryl's referring to is that I have a paper that's been accepted to AppJ, but I have not put it on the archive yet because we're planning a press release with the JPL media team for the paper. And so it's going to go on archive and be published, and the press article going to come out kind of all on the same day later this month. But I wouldn't say that it's not so sensational that it's like heavily embargoed or anything. It's a press release about my paper and my result, and also the larger Stray Cats team. So let me see, doing internet things on the fly almost never works, but let's see if I can pull up the paper and show the first figure, because that would be really nice. The Stray Cats project stands for the NuSTAR Stray Light Catalog. And of course, cats are great. And NuSTAR stray light is actually a contamination effect. It's a bad thing if you're trying to do focused observations. And so this figure that shows 8 different panels are all different examples of stray light with NuSTAR, where the stray light is the big, roughly circular pattern that's kind of coming off the detectors. It's the large green circles in these regions. So if you were an observer asking for NuSTAR time and you received this observation, you might be kind of upset because there's all this extraneous photons all over your detectors and contaminating your source emission. And so then you would need to go through a lot of extra steps to clean this data, to get a valid background, to kind of remove this contaminating source from your source. And it's very much been seen as a nuisance. Now, the reason this happens with NuSTAR and not some other X-ray telescopes is because of NuSTAR's construction. NuSTAR has its mirrors and focusing optics on one end, and then it has a 10-meter open mast and the detectors on the other. So when NuSTAR is pointing at an object, if there are bright sources nearby, I believe it's like between 1 and 4 degrees away from the target, that light can, from these nearby bright sources, can fall on the detectors without ever having passed through the optics. So that's why the image is blown out. It's like if you looked through a telescope, but it wasn't in focus, and you see these giant big donut images. It's just light that has completely bypassed the optics and fallen on the detector. It's really interesting, though, in its own right for essentially 3 main reasons. The first is that because it doesn't pass through the mirrors and the optics, it's not subject to the energy cutoff that the mirrors are. So the only limit as to what photons you can detect is the capabilities of your detector. So for NuSTAR, that means now these stray light photons could be up to as high as 200 keV, when NuSTAR is only rated to look at photons up to 80 keV. So you can all of a sudden key into this really new high energy spectral regime with bright sources, which is very exciting. So that's reason one. Reason two, when you look at something in stray light, the number of photons you're getting is less because it's out of focus. You're not properly collimating all of the emission from the source. And so if you have a source that's incredibly bright, so bright that it's, say, overwhelming the amount of onboard memory for photon counts that you have, using stray light is actually a viable way to observe bright sources without completely missing your data because the telescope is overwriting its onboard memory before it has time to downlink your data, which is bad. If that happens, it's gone forever. So there are some times when you can do a stray light observation on purpose to get more information about a bright source that might ordinarily cause new star some problems. And then finally, three, and this is what my paper focuses on, is when you get these stray light observations, they're often not planned. They're often just serendipitous observations. It's like getting free data to check in on your favorite bright sources. And this is all stray light of SMC X-1, which is highly variable in its timing properties. Why wouldn't we make the most of checking in on this source when we've got the data to see what it's been up to? So it can be a great way to kind of add data to a monitoring campaign. So anybody who's interested in maybe working with stray light data, there is a full functional catalog up on GitHub. We list all the sources that are available in stray light. There is a Jupyter notebook that tells you how to download the software off of GitHub and how to run it and analyze these observations. It's not that bad, really. I mean, if you can do HeSoft, you can do this. And this paper finds just some really interesting timing behavior in SMC X-1, and hopefully it'll be on the archive by the end of the month, and you all can read it.
Amazing. Thank you. Totally impromptu and on the fly. Thank you very much. That was great. I appreciate it.
You're welcome.
Awesome. Well, thank you for joining us, and we'll let you go now, but it was great.